My name is Ed Armstrong, and today I'll be presenting to you Effortless Parallelism, leveraging Julia threads for high-performance scientific computing. Now, the title of this presentation comes from the fact that threading in Julia can be achieved with just a few lines of code. You can walk away now and know how to do threading in Julia, but you wouldn't necessarily understand it. Behind the scenes, Julia creates a lightweight task, assigns it to a thread, and gives it to a clean CPU context, its own stack and register set. But unlike full processes, it shares memory with your main program, and that's why threading is so fast, but also why thread safety matters. So with just the spawn macro and fetch, it really can feel effortless. So the first half of this presentation, we're going to focus on what a thread is and how it works, the hardware background. And then for the second half, we'll deal with some code examples on how to spin up threads and how to use some of the different functionality regarding threads. So how a computer do? A brief description of computer architecture. Most computers consist basically of a CPU and RAM. The CPU stands for Central Processing Unit. It's the brain of the computer. It does all the thinking and calculations. Whenever you run a program, the CPU is what processes the instructions. And we talk about RAM or memory, stands for random access memory, and it's the computer's short-term memory. It temporarily holds data and programs that the CPU is actively using, so you can get to them quickly, or so it can get to them quickly. When the power is off, RAM forgets everything. Now, connecting them is something called the bus, and it's a communication system that transfers data between components like the CPU, RAM, and other hardware. It acts like a set of roads or wires that carry data, addresses, and control signals. RAM holds data like variables, arrays, strings, and such. And here we can see that the string hello is held in memory. You have the memory addresses on the left and the data it contains on the right. Now, RAM doesn't just store data, it also holds the actual instructions that your CPU runs. When a program is loaded, its code is copied into RAM, and the CPU fetches each instruction from there one by one. Meanwhile, the CPU has its own small, fast storage called registers. These contain critical information like program counter, temporary registers here are R0 through R3. That's just for holding data. And then SP has a stack pointer, which points towards your local program data. And this is where all the active computation happens. Now, inside the CPU is something called the ALU, or Arithmetic Logic Unit, and it performs the math and logic operations on the data in its registers. Now, we're going to run a simple mock program for a computer to kind of provide a framework for threading. We have the CPU here on the left that we just showed, and your memory on the right. There's a program counter, it points to 0. And we have a stack pointer, which we'll use in a bit, and it points to the bottom of the stack. Usually the program data and the stack live in quite different areas, and these are all just kept on the CPU. They're kept in a CPU register. So we're going to walk through our toy program here step by step. So the first instruction here, the CPU loads values into registers. So this thing that says R00X A0, all that means is look at the address at A0 and copy that into register R0. So we'll do that now. Immediately after the instruction executes, the program counter increments to the next instruction, and we get to instruction at hex 2. And we do the same thing. So it says R1 with the 0x0c. So that means look for address 0c and copy the contents into register R1. And of course, increment the program counter. Next, we have an add R0. So what that means is we're just simply going to add the contents of the two registers and put the results into R0. Now push R0 here, we're going to work with some local memory. Local memory is your stack, and it's going to push the contents from the R0 register onto the stack. We'll decrement the stack pointer. And of course, after each instruction, we increment the program counter. The final instruction is stop, and this halts the CPU, and we leave it into a final state. Now, this is a fairly rudimentary explanation of how a computer works, and probably some of you here already know this. But there's a takeaway here, and what I want you to take away is this. At the most fundamental level, a running program is just a combination of two things: the contents of your CPU registers and a portion of your memory. The CPU registers, like the program counter, general purpose registers like R0, R1, and the stack pointer, all hold values that the CPU is actively working with. These are small, very fast storage locations built directly on the CPU right next to the ALU. They track things like which instruction we're on. The general purpose registers are for data, and of course the stack pointer, as I mentioned, is for function calls and temporary storage. On the other side here, we have memory, and this is our RAM, and this is where the code and data is stored. Every instruction from the CPU is fetched from memory, and most operations either read memory or write to memory or perform math. So if you could pause a program as it's running inside your computer, you'd find that the state of the program is captured almost entirely by what's in the registers and what's in memory. And that's it. That's your entire program right there. And this is a powerful mental model, because once you understand this, parallelism, consisting of threads, context switches, and shared memory, becomes a lot easier to reason about. You're just dealing with different sets of register contents and memory regions being swapped in and out. Now here we're going to take a look at what happens when a single core CPU multitasks. And this is your base for threading. This is the kind of computation that has allowed computers to run multiple programs for decades. Makes it look like they're running everything at once, but in reality, they're just context switching. So a context switch is when the CPU stops running one program and switches to another. And in order to do that, it has to do a couple of steps. The first thing it does is it stops the processing of the active program. It'll then save the state of the registers and the memory. Then your other program that you want to run is swapped in with new CPU register states and new memory. And then it starts to resume the process all over again. And that's a context switch. That means you're switching context from one process to another, or from one thread to another. Context switching is the action of swapping processes, and it allows multiple threads to share the same hardware. Multiple threads can either be running in one program or across many processes. And now context switches are slow. They're the primary source of slowdown when running multi-process software. They actually take quite a bit of time to go from one process to another. Now, to yield a thread, how does it decide when to do a context switch? You may either voluntarily yield with a command like yield. You'll see me use sleep in my examples, and that will sleep for a guaranteed certain amount of time and promotes a context switch at that point. The operating system may also force a switch preemption, which usually occurs during I/O waits. And that's when the operating system will decide when to switch between different processes. We're just going to briefly talk about memory access and paging when a context switch happens. This is a picture of a Xeon processor. It's kind of neat. So this is one of the first good multi-processors or multi-core processors. And you can see you've got RAM on the right. It's very organized. And you can kind of see a mirror image here in the CPU, and that's your different cores taking place. That's just an aside. Just an interesting look to see that there is a hardware, a physical mirror for what we're talking about. So memory is not just blocks, or is not just one mega block of memory. It's broken up into small fixed blocks known as pages, and they're usually about 4K in size. Each process gets assigned its own set of pages so that when it writes to memory, it thinks it's looking at a whole memory block, but in reality, it's just looking at one section of it because a program typically doesn't use all of your memory at once. So here we have the memory broken up into various pages. Some of the pages are reserved for the kernel, and that's how it tracks which applications are currently running, and the rest are assigned to various programs. While an application is running, it's going to read and write from its set of assigned pages. When the OS pauses the application, it's going to store the contents of that into kernel memory, and the second application is made ready. And it's going to write to its own set of pages so that they're kept separate. And that's how application runs. And now application 2 will write its stuff back into kernel memory, copying application 1 back out. And that's how the contents are swapped and kept in memory. Now, the takeaway here is that all applications, whether you're a word processor or a browser or a high performance computing application, they all share the same physical memory hardware. The switching between processes, when switching between processes, the system has to save and restore the entire memory map, and this is expensive and slow. But threads, which we refer to as lightweight processes, use the same address space. So if you have multiple threads running on the same process, they're all going to share the same memory. That means that there will be no memory swap between threads, just register and stack switching. It's faster, much more efficient, and is ideal for a more fine-grained parallelism. And that is basically the reason why we're using threads and not just running a whole bunch of programs that communicate between each other. Much faster under the pretense that you have to be on the same hardware. So this isn't distributed computing as it's symmetric multiprocessing or shared memory computing. So now we're going to talk about spawning tasks. We're going to get into the code example portion of this presentation. And this is how Julia lets us break work down into smaller pieces that can run independently on the same thread or across multiple threads. This allows our programs to stay responsive and do more than one thing at once. Julia tasks, so the @task macro, they are not inherently threaded. They are known as coroutines, which are functions that can be paused and resumed. Green threads, you'll see them called, which are threads that are managed by Julia. Threads are normally managed by the operating system. Or lightweight threads, as opposed to a lightweight process, and they are much more cheaper to run than operating system threads because there's no context switching. They're not necessarily changing the contents of the registers every time. So that's to say Julia tasks let you manage concurrency without the overhead of real threads. By switching between pieces of code cooperatively, they're ideal for input-output I/O heavy or asynchronous workflows where you don't need real parallelism. So you can spin up a task, you can do things at the same time without worrying too much about the interaction. And we're going to briefly cover tasks before moving on to threads, because in Julia, threads make use of tasks as a base. So here's the @task and how you get it. So the @task macro, so the @ means it's a macro, takes your code and wraps it into a zero argument anonymous function. So it's going to take whatever function I've passed in and further wrap that into another one. And this is key because the tasks in Julia are designed to run independently and not take input directly at runtime. So you're not actually running that function, you're wrapping it inside another one. So @task, or the task macro, is just a shorthand macro for calling the task function. So there is a function called task, which take arguments. And if you're familiar with the anonymous function, or I guess what they would call in other languages lambdas, you pass in the function as an argument. So it's a first class function. It keeps things cleaner, especially when you're quickly spinning off work. So if you just want to spin off something or you want to run something while you're waiting for an IO, that's when you're going to take a look at just a raw task. A common mistake when using a task is that assuming the task macro runs the function, and it doesn't. It just creates a task object. You have to explicitly schedule it or call and then call fetch to get to explicitly schedule it to run it and call fetch to get the results. Now, lastly, task capture variables from the outer scope. This is known as a closure. This means that anything defined in a scope outside of the task, usually defined before the task, is created and still accessible well inside of it. So you can use globals, which is going to be some of the problems that we'll run into when doing shared memory processing. So I'm just going to do a quick little task demo here. We'll start off and we'll go into the Julia REPL. And we are going to we're going to create a function. We're just going to create a simple function called foo. And foo prints out to the command line, I am foo. And so we've created a function, generic function. And what we're going to do is instead of running that function, like we could run that function just by calling it, right? And this is a simple toy function. It's not something you'd normally task out. But let's create it. So we'll call it T1 for task1 at task foo. Notice we don't just pass the function name. We're executing the function, putting the function as an executed function. And what will happen is nothing happens yet. It returns a task variable. We have to actually schedule that variable with the schedule function, pass in the name of the task that we gave it, which was T1, and now it runs. So it says I am foo, because I didn't do new line, it just stops there. And task done. If you want to wait for it, so say it's a long running task and you don't want your program to exit prematurely, you can use wait T1, and that will wait for that task to complete. Since the task is already obviously completed, nothing happens. It just exits the wait function. Now note, if I schedule T1 again, we get an error. A task is only runnable once. So you'd have to create a new task, and we would go T2 is equal to task, schedule the task T2, and wait T2. Now we'll use fetch this time, and the difference between fetch and wait is fetch will return a value if there was one, but they both wait for the process to finish or for the task to finish and then exit. So we're going to look at a slightly second way, and this is just going to be starting our basic introduction to threading. So let's create a, what did I call this? Task demo.jl. So the first thing we're going to do with this, let me open up my notes here. You should be over there. These Zoom screens are taking up all my screen space. There we go. So the first thing we're going to do is create a function that we're going to create that is going to be fed to our task. We'll just call it demo task function. We're going to pass in a value to it because we want to see us passing values into the task. It's going to simply do a short iteration for I in. So we'll run 4 times. And what we're going to do is each iteration, we're just going to print a line giving us information about what task is running and what it's running on. So the ID, which would just be some unique ID that we gave it, a print line on thread. This function, thread ID function under the threads library, it tells us what thread we're currently running on. The main thread is 1. All other threads are some other number. Since we're running in serial code or we're running sequential code, we're only running on 1 thread. But we're still going to print it off just for the sake to be pedantic. We got another function here called threads.endthreads, and that tells you how many threads are available. In this example, it should hopefully be 1. And then step I for the current iteration that we're running on. We're going to use the sleep command here because this is such a it's such a small function that it's not going to take any time to run. And by the time it gets scheduled, it's going to immediately run and it's not going to give up control. So in order to force it to give up control, we use sleep. We need to create the task for it. So we'll create a task for H1 at task, demo task, and we'll give it a number. Now note, as I mentioned before, each task is a new task and it calls the function again. So that's a new call of demo task for each one of these. So we're just going to call it 3 times. Tasks are not explicitly scheduled, so we have to call schedule. And we will call wait. In this case, it probably wouldn't matter, but in the case that a task takes longer to run than the rest of your main program will exit, and you have to wait for the task to actually complete in order to get your results. So that's assuming I have typed everything correctly here. Let's run it. Oh, I'm still in the REPL. We are going to go Julia, task demo JL. Oh, I typed everything correctly. Oh, except for the ID. There we go. So they run in order 1, 2, 3, 1, 2, 3, 1, 2, 3. Because they run and then give up because it's running on one thread. Of course, thread 1 of 1. So there's only one thread and it's the main thread. And then we just do it 4 times. Now I'm going to introduce this command line flag now. Minus minus threads equals 2. And that will run 2 threads. So you'll see it now says 1 of 2 because we have 2 threads available. But because we're running a task and we're not running a thread yet, it's still running on thread 1. And you can do this for as many threads as you want. I've got 16 physical threads on this computer. It doesn't care. You can do 1,000 because threads are just a concept. You don't need to have a physical core to run the thread because it's essentially just a lightweight program. So returning, let's move on. So schedule. So this is what we did. So we'll quickly recap what we just saw. We used the task macro. Oh, I've lost my pointer. Where'd my pointer go? There we go. We used the task macro to create 3 tasks. But that alone didn't make them run. We had to call schedule. We explicitly called schedule to hand those tasks over to Julia's task scheduler, and that's when they became runnable. We then used wait to pause the main program till each task was finished. Without wait, the main thread could exit before the tasks are complete. And even though we had multiple tasks, notice how some of them ran on the same thread. This confirms that Julia's tasks are cooperative. They're not parallel until such time as we spawn them with threads. In addition, we got 2 new useful calls. Endthreads shows the number of threads available, and thread ID tells us which thread we are running on. This allows us to check to make sure that we have actually enabled threads. So when you're running a program and maybe it's not speeding up the way you want, print off the thread count, make sure you actually have more than one. If you want to see more than one thread in action, we need to start Julia with the extra threads. And you can do this by using the thread flags on the command line. Now, we've seen cooperative tasks. Now we're going to get into real concurrency. The spawn macro creates and schedules a task that runs on any available thread. It's simple. You write the work the same as you did with the task and fetch the result. This is really where the title for our effortless parallelism comes from. On the surface, threads in Julia are 1 line. 2 if you want to wait for the result. The actual thread creation is effortless. Now, take note, as opposed to the task in Julia, you cannot manually assign the task to a specific thread. You have to use the @spawn and it does the assignment for you. A regular and also the regular task macros need the schedule function. The at spawn will create the task and do the scheduling for you. So you don't have to call schedule with this one. They're cooperative because they always run, tasks always run on the current thread, and then threads are scheduled. Now, this is the simplest and safest way to tap into threading power, and it's perfect for CPU-bound workloads if you want to split across multiple cores. So this is just a quick little diagram to show the visual difference between a task and a spawn. On the left-hand side here, we have a task macro. So it runs the main thread, starts up task number one, has to wait for it to yield until it can start task number two. All tasks run on one thread without parallelism. When we use that spawn, the main thread is going to start up each task in turn, and they're all going to run concurrently on available cores on multiple threads. Now, before we move on to a code example here, we're going to talk briefly about loop parallelism. And this is the second main way of starting threads on Julia. The @threads macro will split loop iterations across threads automatically. It's fast, it's easy, it's great for embarrassingly parallel problems like filling arrays or doing independent calculations. Now, in this example, what we have is if you ignore the @threads part, this is just a regular everyday Julia loop that goes from 1 to 10, and it's going to assign it to some array, the thread ID that it happened to run on. And you could run this and you could see how the loop parallelism spreads out your calculations across different threads. Now, when to use loop parallelism, when not to use loop parallelism and use regular everyday threads. Loop parallelism is easy and it can be added to just about any code that has a loop, assuming certain conditions are met. It's not always a plus. It's not always a win for your code. If the iterations depend on each other, so that means if one iteration of the loop is using a value that was set by a previous iteration, you can't use this one because it's going to split them up and they have to be independent. If the loop is too small, and we're going to see that in one of our examples, your threading is going to hurt more than it's going to help. Because of the overhead between context switching and protecting your data, it could possibly slow down your code. Because if you need to be doing a significant amount of work within the loop in order to take advantage of parallelism. And if you're working across machines, you'll want to use the distributed tool. So this is not used for multiple nodes. You're going to be limited to the number of cores on one node on our clusters or the number of cores in your desktop. For distributed memory environments, you would use the distributed package, which is beyond the scope of this presentation. It'll be another one. So yeah, you need non-dependent loops. So each loop has to be independent of each other and not small loops. Big loops is what you want here with a lot of computation. So now we're just going to do another little demonstration here. And I will do, that's not my new, there we go. So we are going to do a parallel sum. So the first thing we're going to do with this code segment is we're going to bring the threads namespace into local scope. That's just the using base.threads. This is not necessary because threads is a base package. You can just use threads dot, but this way we don't have to prefix everything with the package name. So what kind of function are we going to do? We're going to do a partial sum. So what this will do is this function counts everything or sums up everything between start and stop. It's a simple little function, basically add up all the numbers from 1 to 10, add up all the numbers from 100 to 1,000, so on and so forth. Now we want to print out just the exercise here is to see how the loop spread or how things are split up. So thread will print out the thread ID. Note I didn't do threads.threadID this time because I've got the using up top. Summing from, so we'll just look at our start value to our end value. And we are going to return the sum. Now, sum is not mine. That is just a built-in math. But that's going to be run within a thread. So it's a function that calls a function. And that is not end, that is stop. So first thing we're going to do is we want to divide the work. So divide the work. If we have something, we're going to basically just create a number of iterations based on the number of threads we have. So threads, we don't have to do threads, end threads. And we are going to do a chunk size. So we're just going to, for every thread, we want to count 25 million. So if we got one thread, we'll count up to 20, we'll sum from 1 to 25 million. If we got two threads, we'll sum from 1 to 50 million, so on and so forth. Now you typically would not, in the previous example, I just gave each variable T1, T2, T3, a thread. Normally you would assign these tasks or these threads to an array so that you can have a variable size. You can change the size at runtime, allowing you to try different makeups. And that's why we have the tasks array here. So we're just going to store the tasks into there. So from I in 0 to, so for the number of threads we have, start is going to be the beginning of it, the chunk size. Stop is equal to, that just tells us where to start and stop each one. So basically we're dividing up a count between 1 and 100 million across 4 threads. Push means we're going to push the value onto the tasks stack. And we're just going to spawn this. So because the macro allows you to just, it returns a value, it almost acts like a function. We are going to pass that as a variable, or sorry, as an argument into the push function. Partial sum is what we call our function. Start and stop. Note and end. We've already got end. And at the very end, once we're done, we need to wait to sum the results. So this is a divide and conquer strategy. And you would normally have a lot more computation going on there than just doing a simple little sum. But the basic framework, the skeleton of the program is the same. Create your function, divide up the work, bring it back in, merge the results. So we are going to go total is equal to sum. Now in here, you're going to see fetch. So fetch means this returns a result. Our previous one didn't return a result, so we used wait. Now we're using fetch. Fetch dot means apply it to an array. So it's an array of tasks, and our tasks are there. So that will sum the result into here. So that's your divide and conquer. Divide it into smaller chunks, sum it up, and then resum all the results. We'll print line total sum at total. And let's see how my typing did. See if we got any typos. So there we go. So Julia, we're going to start with the basics. So without anything, it's going to run on one thread, and that's just what we're going to do while we make sure that we have coded this correctly. Oh, we got an error. Of course I do. Expect, oh, didn't close something. And the best way to do that is just to copy my notes. Where's that unclosed? All right, on the push. Push didn't close. There we go. Let's try you again. There we go. So you sum one thread from 1 to 25 million, and that's the result. To change this, we're going to go with tt -- threads equals 2. And now we will run, oh, no spaces, sorry. And now it will sum from 1 to 25 million on the first thread, and from 25 million and 1 to 50 million on the second thread, and that's our sum. You'll notice when I did the error up here, it says Julia -t or -- threads equal. And you can do -T for the number of threads you want. So we'll just go -T4 in this case, and it will run 4 threads. Oops, forgot my program name. Try that again. -T, no equals, just 4. And it will run it. 8, so on and so forth. You should be able to go --threads equals auto. And that will use every thread available on your system. I'm running a 16-core computer, so I've got 16 threads available. And that just automatically sets your number of threads to the number of cores you have, which is more often than not what you want to do. Another important note is we did just do that, and if I exclude or don't include the file name, we're going to start up the REPL. And I should be able to go threads.endthreads, and I have 8. So you can also run the REPL with multiple threads, which is really handy for, testing things out. The next we're going to look at is loop parallelism. Now, loop parallelism usually ends up being much more simple programs. As you've met the preconditions, you don't have dependent loops and usually a significant amount of computation. For ours, we're not going to have a significant amount of computation because we're just doing little toy programs. But that's kind of deliberate because I want to show you the slowdown from using threading when you shouldn't. So we're going to start by creating an array of zeros. Array of integer. So we have 1 for each and thread. An array of the size and number of threads we have, all filled with zeros. And all we're going to do is we're going to go at threads. So we have the loop for I in 1 to 10 million. What we're going to do is we're just simply going to increment inside that array to tell us how many times that particular thread was utilized. So that's all we're doing. We just got an array of zeros incremented each time the thread is called. It's 1 in 10 million. We expect it to be fairly evenly distributed because there's almost no work going on. Enumerate, thank you. Now what this is going to do is we're just going to go over the array we created, and we're going to print out how many times. So how many times it was called. So thread I handled count handled count iterations. Of course, count is a variable. Pulled from here. And let's have a look-see. We'll start, of course, with 1. Takes a second to compile it first, and you will see 10 million iterations, all handled by thread number 1. Let's double our number of threads. Split in half, 50 million each, or sorry, 5 million each. Again, so you see it's fairly well distributed for quick programs, just like that. And that is simply how you do, simply adding this in front of the loop gives you loop parallelism. If we take that out, then it should not split across threads, right? So we got 8 threads available, but because we took out the loop macro, it all went onto the main thread. So that's the 2 things you need to do to actually launch a thread. But now we're going to talk about thread safety and synchronization. And this means understanding how to safely share data between threads running concurrently. Without proper synchronization, threads may read or write shared variables in unpredictable ways. So this leads to race conditions, corrupted states, or deadlocks. So we're going to cover race conditions, or what happens when threads access shared data in an unsafe manner. Locks are used to prevent this simultaneous access. Deadlocks is if we go a little too crazy with locks and too many locks are running at once. And then we're going to look at, time permitting, atomic operations, which is a simple and fast thread-safe alternative for updating simple data. So a race condition. A race condition is what happens when two threads access or modify the same piece of data at the same time. And the outcome depends on the timing, on which thread does what first. It's called a race because both threads are essentially racing to complete their work, and whichever one gets there first determines the result. The problem is that this creates unpredictable behavior. Sometimes everything works fine, and other times you can get wrong results, crashes, or corrupted data. And these bugs are notoriously hard to track down because they don't always happen. You might run your program 100 times and only see the issue once. That's why avoiding race conditions is a key part of writing safe multi-threaded code. We deal with race condition using synchronization tools. In our example today, we're going to be using locks and atomic operations. And this makes sure that only one thread can catch a critical data at a time. But first, here's an example. This is a classics example of what a race condition is. Say two people, a teller and an ATM, are trying to withdraw money from a bank account at the same time. This is a normal transaction. In a normal transaction, you would look up the balance. It's $100. You would calculate the balance minus your withdrawal. So you do $20 and you update the balance and write back so that the bank account now contains $20. And it's critical to note here that these are three discrete steps in this process, and they don't all occur at once. They could have quite a bit of time between them. So let's take a look at what happens if two people, so say on the left is our teller and on the right is our ATM. You could look up the balance. The teller looks up the balance, says he sees there's $100 there. The ATM also sees there's $100 there. The teller calculates what their new balance is. They say the new balance is 20. The ATM says, well, our new balance is going to be 30. Teller writes it back to the account, says, here's your $80. You now have $20 in your account. And the ATM says, oh, here's your $70. You now have $30 in your account. And what has happened here is we've withdrawn $150 from a bank account that only had $100 and had $30 left. So this is completely miffed up. What we need to do, what we have here is a race condition. In a race condition, it occurs because there was two threads or two things using the same data at the same time. Now, race conditions don't only exist in threads, they also exist in databases and really anywhere where these three conditions are met. You have a shared resource between two things. You have concurrent access, so they can both access at the same time, and one of them has to be writing. If everything is reading, you're not going to get a race condition. If at least one of your threads or one of your processes are writing, then you have the chance of a race condition. This is an example of a race condition, and we'll run it in code in a moment. And what is happening is we've used thread parallelism here to increment a global counter each time. But because global counters, the plus equals operation is not actually atomic. It does not occur in one step. It occurs in multiple steps. So we would expect to see different values depending on whether we're running that threaded or not. So let's go take a look at that real quick. So we'll call that race conditions loop. For the sake of brevity here, I'm just going to copy and paste and we'll explain what's going on. Exact same thing we just saw on the slide. Now we got loop parallelism. We're going to count from 1 to 10 million in this case and do a global counter. Note, remember that if you've got a global variable and you want to update it from a function, you must include the global keyword. And then we'll print the final counter value. And we're going to have a time on here. The at time macro just tells us how long it took to run things. So let's start with one thread, race condition loop. So we would expect no race condition to occur with one thread, right? Because there's only one thread operating. Took about 1/4 of a second to count to 1,000,000. Let's add a second thread. Immediately, almost half, because it's so fast, because there's so little work being done, the threads are just zooming through. And we got very little speed up and a completely wrong answer. Do it again, we'll double again. You can see it's more or less 1/4, but not exactly. And if we run it different each time, we get a different number each and every time. So while we're getting a little bit of speed up, it's at the cost of program correctness. Do 16, we get a much different number. So that is a race condition. That is a race condition live. Because I'm spreading out the calculation over multiple threads, they're updating the global counter at the same time, which creates many problems. So what's our fix? Our fix is a mutex, which stands for mutual exclusion lock, or sometimes called a reentrant lock. You are entirely responsible for ensuring your program is data race free. These things aren't automated, and nothing promised here can be assumed if you do not observe that requirement. The observed results can be highly unintuitive and hard to track. An important tool to avoid these, of course, is the lock. And a lock is, by its name, can be set, locked, or unlocked. If a thread locked a lock and not unlocked it, it's said to hold the lock. If there is only one lock and we rewrite code that requires holding the lock to access some data, we can ensure that multiple threads will never access the same data simultaneously. Note that this link between lock and variable is made by the programmer and not the program. So up here, it's called a reentrant lock, and that just means that if you call another function and you call this function again, if that thread already holds the lock, it will have no problem continuing with the critical code. With more vanilla locks, if the same thread tries to call the same lock twice, then it will block itself. So we typically use what's known as a reentrant lock that allows a thread to enter the same critical code segment multiple times. I've called it a mutex. I just like to call my locks mutex because particularly when they mean it's a mutually excluded part of code, mutual exclusion lock. And this is what the lock does. It's just a nice little demonstration of what's going on. Thread number 1 runs. Once thread number 1 acquires the lock, it can run with code that's in the critical section. And then it releases the lock. Once it releases the lock, code starts running in parallel again. And thread number 2 can acquire the lock and release it. So just to reiterate here, notice that they run together until such time as they both want the same lock. Then one runs at a time, and then the rest continue. So one more demo. So let's take a look at race conditions. So this is our original code with the race condition, and we are simply going to create a mutex for it. We are going to call lock. It's literally called lock on the mutex. And down here, we are going to unlock the mutex. So that creates this section, that creates the global counter incrementation is now our critical code segment. And that means that because it's protected by a mutex, only one thread will run it at a time. So let's take a look. Now, if we run it with one thread, we would expect same results as before. If we run it on 2 threads, we've got the correct number, 10 million, whereas before it was half. But note, it's taking longer to run. And that is because we broke, I do believe it was rule number 2, which is you have to, with loop iterations, or really with any sort of parallel code, you have to be doing a significant amount of work so that you are doing more work than is eaten up by the context switch. Because every time the mutex hits, there's computation going on. Notice we're almost double the speed, more than double the speed when we double the number of cores, and we just get into a serious contention issue. And this was done by design because I used a simple incrementation counter. Another example I've got on hand here, and I will just, this is my bank example. And this is the example that we just showed in there. But again, because I'm running short on time, we're just going to copy and paste it over. So what this will do is it wants to do some operations on some shared code, and we're going to get a different result every time. Oh, why isn't it printing out? There we go. But if we do minus T4, oh, there we go. Now notice I didn't get it the first time. I ran it twice and I got the same number twice. Run it again, you get a different number. Now again, that is because we've got a shared data, which is balance. They're accessing it concurrently, and at least one of them is writing. That's where the global balance is equal to new balance write takes place. But I want to talk about atomic, so we're not going to talk about, we're about done with race conditions, except for one problem. And this is multiple locks. When you have multiple locks, you need to be careful you don't get what's called a deadlock. Now, this is kind of hard to demonstrate in code because it literally grinds your program to a halt. And then all sorts of hilarity ensues. So we're just going to demonstrate it with a diagram. If we have two threads running and both threads are accessing data, but we have two different locks and we access them in different order, thread number one will acquire lock A and thread number two will acquire lock B. But when thread wants to get B, thread one wants to get B, and thread two wants to get A, everything grinds to a halt because they're locked. And this is what a deadlock condition is. And the rest of your code simply never runs. Now, these are actually fairly rare because if you follow best practices, it shouldn't happen. You can only get a deadlock if you use multiple locks. So that's why we say start with a coarse-grained approach. Start with one lock. And if you need more than one lock, use more than one, only in the case that you do. Try not to hold locks across long operations like I/O. I/O is better for a task than it is for a thread anyways, and you should be using asynchronous programming as opposed to synchronous threaded programming. Always acquire locks in the same order. So when we did this demonstration here, we acquired A and B in one thread and B and A in another. If they both acquire A, then B, you won't have a deadlock situation. However, sometimes maybe you do need multiple locks. Those would be a much more fine-grained approach to parallelism, and you're going to have a lock over maybe 100 different pieces of data. In that case, you should use what's known as a lock manager or hierarchical locking, which will enforce order and queuing. If your locks have some sort of built-in orderable value to them, you can order them before locking them and thus get rid of your deadlock problem. And of course, you limit your concurrent access and minimize threads. Don't just throw threads at everything to try and speed it up. As we've seen, sometimes it'll slow it down. And if you're sloppy, you can get yourself into a deadlock situation. There is one more thing, and this is pretty good for avoiding deadlocks, but in much the same way that you had that loop parallelism was for a more simple case than regular threaded parallelism, using atomics is another simpler case. So if you've got the situation that you just want to protect one variable and you're doing very simple math on it, you don't need the full weight of locks. It's just a safe way. There's a safe way to increment the counter or set a flag, and that's atomics. So here, atomic is, it looks like a number and it works on numbers. It doesn't work on complex objects, but you just call the atomic keyword and you pass in a generic. So that's a type specifier, and it will return an atomic type that acts very similar to a number. They are incredibly fast. They are usually CPU supported. So your CPU actually has atomics on it. And that just means that it does the whole operation at once. And if you do an operation all at once, you can't have a race condition because there's no operation to split up. Now, they're not magic. They only work for simple values and they won't help you coordinate more complex read, write, modify patterns. But for that, you'll still need locks. But if you want to do a counter, here's your answer. Now, there's a couple of operations you can do on it. So the top here is how you declare it. You do an atomic add. You have to put in X is the lock, and you add value to your lock. Subtract, you can subtract the value from your lock. You can exchange a value from your, sorry, not your lock, your atomic. You can exchange the value for your atomic. And CIS is check and set. Check your atomic for the expected value. If it's the expected value, set it to the new value. And we are going to do one more brief demonstration. We're just going to rewrite that last code we did with atomic. So we got the problem here. This is race condition mutex, right? We fix it. There we go. We fixed the race condition with the mutex. Instead, we're going to fix it with atomics. So let's go back to our original. So this was the original problem code in that the global counter is shared across threads. So instead, we are going to create a counter is going to be atomic. So it's the same variable name. We're going to make it an atomic with the generic integer and set it to initial value to 0. Instead of this, instead of accessing it globally, we are going to call the function atomic add. Pass in the counter name, which is counter, and the amount we want to add to it, which is 1 because we're incrementing. So as before, we're going to run it again. Let's start with one thread, same as we did. Right, still counts up. Now note we've got to set a different value. It's no longer just prints out the number. I do believe if you want to print that out, you can do this. We'll access it as the actual number as opposed to an atomic. Right? So now it's not printing out the object, it's accessing the guts of it. And it ran in a certain amount of time, 0.03. Runs faster the second time because of Julia's just-in-time compilation. But as you'll recall from before, it slowed down when we added more threads when we used a mutex. So let's do 1.32. Oh, still slowing down a bit. Well, it lied to me. What did I do? Well, that's an atomic. So that puts us right at exactly 1 o'clock. Thank you very much. And I will ask anybody wants any questions. I will briefly go through the chat and see what showed up.